This is second video on design of gearing related to Spur gearing. In the first video, I gave the brief introduction of Spur gearing, its uses and limitations. Then we discussed the forces coming on the tooth and type of load, followed by the modes of failure, and finally we ended the first video with the development of beam strength equation. The Lewis beam equation, which was developed in the first video on Spur gearing, consisted a factor y which was termed as Lewis form factor. It was mentioned that the form factor is a function of number of teeth on the gear and the pressure angle. Further, it was mentioned that gear tooth profile is involute. In the present video, the pressure angle and involute profiles will be discussed in greater details, followed by discussion on an important phenomena in gearing known as interference, which is related to the involute gear tooth profile. Again, it is to remember that most of the fundamentals which were discussed in the first video and which will be discussed in this video are applicable to all of the gearings with slight modifications, of course. For proper operation of the gearing, the law of gearing must be satisfied. Before I read the statement, please refer figure 1 on the right. In the figure, a pair of teeth is shown in mesh. The driver gear is having pitch circle radius of small r and is rotating at angular speed omega 1. The driven gear has pitch circle radius of capital R and rotates at angular speed omega 2. The point of contact of the two tooth profiles is marked as point P in the figure. NN is the common normal to the two tooth profiles passing through point P. TT is the common tangent to the two pitch circles. The angle between the common tangent and common normal is marked as phi in the figure. This angle phi is known as pressure angle because the tooth of the driver gear presses the tooth of the driven gear in the direction NN. Now I read the statement. The common normal NN passing through the point of contact P of two tooth profiles must divide the center distance O1 O2 into two portions O1P and O2P inversely proportional to the angular speeds omega 1 and omega 2 of the two gears. Since the angular speeds omega 1 and omega 2 are fixed, the two portions O1P and O2P are also fixed. In other words, I would say that point P is having a fixed position on the line O1 O2. Now I discuss the gear terminology. On the left of figure 2 is shown a three-dimensional view of a gear tooth. On the right of the figure, a pair of teeth is shown in mesh. Some of the important terms addendum, dedendum, addendum and dedendum circles, pressure angle, etc. of the gear's geometry are marked, which are defined and discussed in the slides to follow. Pitch circles of the meshing gears refer to the friction mills rolling without slip, which can replace a gear pair giving the same speed ratio, that is the ratio of number of revolutions of driver to that of the driven gear. Refer figure 2 and also figure 1. The circular pitch PC is the pitch measured along pitch circle. It is simply the circumference 2 pi r divided by the number of teeth Z on the gear, where r is the pitch circle radius. Refer figure 2. Addendum circle is the circle which bounds the outer ends of the teeth. Addendum is the radial distance between the pitch circle and addendum circle. Its standard value is 1 module. Dedendum circle, also known as root circle, bounds the bottom of the teeth. Dedendum is the radial distance between the pitch circle and the dedendum circle. Its standard value is 1.157 module. Again refer figure 2. The pressure angle phi is the acute angle between the line of action NN and the common tangent TT to the pitch circles at the pitch point P, as has been already defined. For gears with involute teeth, the pressure angles in common use are 14.5 degree, 20 degree and 25 degree. Beam width or face width, B is the width of the gear tooth measured parallel to the axis of the gear. Refer the three-dimensional view of the tooth in figure 2. Base circle is a circle from which the involute, that is the tooth profile, is generated. It is discussed in the next slide. Now I discuss the involute profile, its generation and its characteristics, followed by interference in gears with teeth having involute profile. Figure 3 on the left shows the involute of a circle, which is locus of a point at the end of a taut string being unwound from base circle. Thus the normal to the involute is always tangent to the base circle. In the figure on the left, 3 normals have been drawn to illustrate that all of them are tangent to the base circle. It is to note that the involute is not defined inside the base circle. It is an important characteristic which will clarify what is interference. A portion of an involute is used for the tooth profile. For example, refer figure on the right, where the blue line is a portion of the involute shown in the left figure. Since the involute is not defined inside the base circle, hindrance in the normal working, called interference, occurs when the involute portion of gear 1 contacts a non-involute portion of gear 2 as shown in figure 4. The interference is highly undesirable and it can be eliminated if the portion of the tooth below the base circle is cut off, as shown in red in the figure. It is known as undercutting. The undercutting weakens the teeth. It has been shown analytically that the interference can be eliminated when the number of teeth on the smaller of the two meshing gears, which is called pinion, is greater than a required minimum. That is, when Z pinion is greater than equal to Z minimum. Z minimum is given by the relation Z minimum is equal to 2 times of addendum divided by module multiplied by sine square phi, where A is addendum. Thus, for the standard addendum of one module, Z minimum is equal to 32 for pressure angle phi is equal to 14.5 degree and 17 for pressure angle phi is equal to 20 degree. For gears with stub teeth, that is addendum is equal to 0.8 module, Z minimum is equal to 26 and 14 respectively. The stress concentration refers to abrupt increase in the stress due to notches, holes, fillets, grooves, and internal defects in the metals. The weakening effect of the stress concentration is more significant under fatigue loading. In the case of gears, the region of stress concentration is on the tensile stress side of the fillet, marked as C in the figure, and it is a matter of concern. The stress concentration effect depends on the shape of the fillet and the material of the gear. It is expressed by a factor Kf defined as Kf is equal to 1 plus Q Kt minus 1, where Kt is known as theoretical stress concentration factor and is a function of the shape of the fillet only. Factor Q is termed as notch sensitivity index and it is a function of the material. For most of the applications, plain carbon steels, carbon less than equal to 0.45% are satisfactory and are economical also. The medium carbon steels are oil quenched. Water quench may be necessary when the carbon content is low, but the distortion of the tooth is higher with the water quench. Alloy steels are superior to the plain carbon steels because of their greater hardness, depth of hardness, less distortion in hardening process, and greater toughness and fatigue strength. Various grades of cast iron are used for low speed gear drives. The cast irons have very good wear resistance, but the fatigue strength in bending is low. When corrosion is the problem, bronze gears are used. The friction with bronze is low, hence it is used for the worm in the worm gearing where the sliding velocity is high. Molded plastic gears may be used instead of metal gears in lightly loaded drives. They transmit power silently and often without lubrication. The phenomenon of interference in gears with involute tooth profile, the minimum number of teeth on a gear to avoid interference, the gear terminology, materials and stress concentration effect have been presented in this video. The discussion presented here also applies to other types of gearings with some modifications. Interference doesn't occur when the gears have cycloidal tooth profile, but unlike involute gear tooth profile, Such gears are difficult to manufacture. In the next video, the application of Levis beam equation for the design of spur gearing would be discussed. The references used here are listed here. It is advised to the readers to refer standard textbooks for greater details. Handbooks of the machine design are quite informative and reliable source of information. Feel free to send your questions at my email address given on the first page. Please wait for the next video. I hope you have liked this video very much. Thanks.